This, I guess you all know me, so no introduction. More than that, this is joint work, very recent joint work actually, with my student Naman Agarwal and my half-student Vivek Madan. He's a full person, but he has another advisor, like typically. So, okay, yeah, he's a full person. Very smart one too, both of them. Okay, so this talk is about expander graphs, and the general sort of layout of the talk would be as follows. First, I'm going to tell you a little bit what expander graphs are. Probably you all already know, but I'll give you the point of view of myself and the field. Then lifts of graphs. What are lifts of graphs? Originally, lifts of graphs were suggested to construct expander graphs. Therefore, I'm going to describe what they are. And then show some results about two lifts and generally small lifts of graphs that prove that most of them are indeed expanding. And thus, this is the right way, or one of the right ways to go in order to construct expander graphs and give some open questions in the area. So expander graphs are great. We all love them and have been, in the last few decades, have had numerous applications in almost all areas of computer science. To name a few: design, algorithms, error-correcting codes, randomness extractors, pseudo-random generators, sorting networks. Other more striking applications in complexity theory, the proof that L equals SL by Reingold, or the new proof of the TCP theorem by Dinur, etc. So the moral of this slide and the story in general is that expansion is good. Therefore, we seek ways of achieving high expansion efficiently. We, as in computer scientists. There's three standard sort of literature ways where we can see what expanders are. There's a combinatorial definition of expansion where we look at cuts or sets and see how much they expand, what are the edges that go out of this set. The other is the linear algebraic point of view where we look at the eigenvalues of these graphs. And I want to say what's a spectral gap. We want a large spectral gap. I'll define what that is in a second. And the third one is probabilistic. So we want random walks on expanded graphs to converge rapidly. I guess we want random walks on graphs to converge rapidly. Expanders achieve that. So really briefly, the combinatorial definition of expansion, what it does, it takes a graph G, and such a graph is said to be epsilon expanding if for all subsets of the vertices, let's say less than half of the number of nodes, the number of edges that go out of the subset is proportional to epsilon times the size of the set. And in this sense, the standard definition of edge expansion, this h of g parameter of the graph, is just the minimum overall cuts, S and S prime, of the edges that cross the cut over the size of the smaller side of the cut. And for the spectral definition, which is what we're going to be interested in for this talk, and they're very related, the two, let's define some things first. Look at the adjacency matrix of G, and then by a matrix, it has n real eigenvalues, and let's order them in decreasing order, lambda 1 through lambda n. We're only going to be dealing for this talk for deregular graphs, because traditionally, expanders were deregular graphs. I mean, there's some sort of new works with sparsification, etc., that try to construct non-regular expanders, but let's just focus on deregular graphs, in which case lambda 1 is always d, and if the graph is bipartite, lambda n is also minus d. We call those two the trivial eigenvalues, so those are always going to be standard and known. And what we really care about, what parameter we really care about, is what we call lambda. So this lambda is defined to be the maximum absolute value of all the other eigenvalues. There are none of the trivial ones. If the graph is non-bipartite, then lambda n is also included there. So lambda is just how big can any other eigenvalue than the trivial one can be in magnitude. And spectral gap, we refer just the gap between the first and the second eigenvalue. In this case, d minus lambda 2. And something we're going to use a bit later, if we want to define spectral radius, this is just the highest absolute eigenvalue of a matrix. So in this particular case, it would be d. Okay? All right, so here is what expanders are. And in the spectral sense, it's quantified largely by the following theorem, which is also known as Tiggers Inequality. It says that what we just saw before, the edge expansion, is closely related to the spectral gap. In fact, it's between d minus lambda 2 over 2 and square root 2d d minus lambda 2. This is a very useful theorem that has led to many beautiful algorithms. Okay, so now, since we're convinced that spectral expanders and edge expanders for us are both very important and are very similar in nature, let's see how much expansion can we expect. And let's see that in terms of the spectral gap now. So expanders for me are large spectral gap graphs from now on. Okay, so we want expansion. We want it to be a spectral gap. We want it to be as big as possible. How big can that be? Well, there is a theorem by Alon and Bopana, very well established theorem, that says that unfortunately, no matter how much I try, for any d-regular graph, I cannot get lambda 2 to be any smaller than 2 root d minus 1 minus some little of 1 that goes to 0 as n goes to infinity. So this is as good as it gets. This is how much I can hope for. And the question now becomes, is that something that's achievable? In that light, let's define a d-regular graph Ramanujan if this is achievable. If lambda is less than or equal to 2 root d minus 1. And it's sort of normal these days to define stuff quasi-polynomial, quasi-exponential, quasi-Ramanujan. Those would incorporate some constant factors or around constant factors. Okay, so here comes the important question that a lot of computer scientists have asked. Well, it's easy to see that Ramanujan graphs exist in very small number of nodes. Take complete graph on d plus 1 nodes, it's Ramanujan. Great. But this is not very useful for applications, if you wanted to build large fault-tolerant networks or something. So the question is, can we find arbitrarily large Ramanujan graphs? A series of graphs that grows with n, and they're all Ramanujan. This question was answered. The answer is yes. And first, Margilis, Lubotsky, Phillips, and Sarnak, and then Morgenstern, with an extension of their theorem, constructed such graphs for all n. The caveat here is that the degrees of such graphs were known so far to exist was d when d minus 1 is a prime number. So this was in the 80s, and in fact this is the only construction of Ramanujan graphs. This group of constructions, I guess, is the only construction of Ramanujan graphs known to this day. So we don't know how to construct such graphs for any degree different than such that d minus 1 is a prime. Okay. However, there are some things that we do know. One is a celebrated result by Friedman that showed that random d-regular graphs are almost Ramanujan with very high probability. So, okay, it's really hard to find them, but if you really just sample randomly, boom, you just get a Ramanujan graph, almost, with some small epsilon, which is great, but still doesn't tell me how to find them. And then there is a recent break.
Does epsilon depend on n or d?
I think it depends on d. I don't think it depends on d.
For every epsilon.
No, but it goes to 0 with n.
Does it? I'm not entirely sure about that.
For every epsilon for sufficiently large n.
I think numerically it's normal for some large percent of the random graph, but not for all of them.
Yeah, I think epsilon is a constant that depends on d.
What's stopping epsilon from being d to the 3/4 then?
Okay, maybe exponential or something in d. But yeah, I mean, fine. Yeah, I didn't mean like a function like equal to d or something. I meant yeah, okay, fine. 1 over 2 to the d or 1 over 2 to the 2 to the d or something
Whereas
like
if
that.
you know, as Gil said, it's with like 52%, the graph will not be Ramanujan.
Yeah, so I'll get to that in a second, actually.
But if you want the epsilon to tend to 0 with n, then it's not known whether there's a Ramanujan graph for every.
I think this is not true, experimentally. I mean, it's not proved.
Probably should be, right? This is 53% conjecture.
No, but it's not with high probability. This result holds with exponentially high probability in n. So if you take a n vertex d-regular graph with probability exponentially small in n, this is not, rather, with probability 1 minus exponentially small in n, this holds.
Polynomial.
Polynomial. asymptotically going to 0 with n. So I'm sorry, I don't know exactly Friedman's parameters right now, but with extremely high probability, a random deregular graph is almost Ramanujan. In fact, this has been improved, which I'm going to mention a bit later, by Putter, that showed +1 here. Doron Putter. Putter? I don't know how you pronounce his last name.
Putter's a weaker result. Friedman showed that that's true for every epsilon bigger than 0. Putter showed a somewhat shorter proof. Friedman
Right, so it's a more global proof that includes what I'm going to talk about next. But let me get to that in a second. So this happens, and in fact, it's one of the open questions: what is the probability that a graph is exactly Ramanujan, which I'm going to get to in the end. But what happened recently, which probably most of you have heard this talk by, Nikhil was here, by a result by Marcus Pillman and Srivastava showed that Ramanujan graphs exist for every degree. This was an existential proof, though, and still didn't give any construction, nor did it sort of say what probability you can find them or anything like that. There was, by Friedman again, a suggestion that came a few years back that just like we build expanders from small expanders by performing some operation, he suggested, why don't we take a good expander and lift it, so create a graph lift, and hope to get a good expander. The suggestion was sort of implicit in the first paper that proved relative expanders with lifts. So let me define what lifts of graphs are. By picture, hopefully, and that should be enough, but we'll see. So here's a base graph, 3 nodes, and a k lift of a graph. Let's take k equals 3. It's a graph that has 3 times, or k times in general, as many nodes as the base graph. So I replace each one of the nodes by 3 copies. And let's number them 1, 2, 3. First copy, second copy, third copy. And I replace every edge with a matching between these sort of blocks of nodes. So in this particular lift, we have replaced every edge with the identity matching, or identity permutation, identity labeling, you can call it as you wish, where the first copy of each of the vertices is connected with each other. In this lift, we've replaced only the purple edge with the identity, and the rest with some other matching, some other permutation. So this is what lifts are for general K, and more formally, we have, if we take a base graph G, the lift has K times as many nodes, K for each vertex of G, and we define this sort of K nodes as a fiber of the vertex V. And every edge xy is replaced by a permutation, a matching, however you want to call it, that connects the corresponding copies of these fibers, indicated by the permutation. By the way, for those of you who know Unigame's conjecture, this should sound very familiar. And I'll talk about the connection there if I have some time. And the opposite edge, just take the inverse permutation, so the yx edge, take the inverse permutation. K would be the degree of the lift, not to be confused with the degree of the graph. I know it's a bit like similar notation. G is called the base graph, H the lifted graph for the rest of the talk. And what we mean by random lifts is if we fix the base graph, fix a K, and choose each one of the permutations for the edges uniformly at random, depending on how you choose them, from what set. But let's say now from SK, the set of permutations of K elements, this is a random lift. If you choose each permutation from the set of shift permutations of K elements, this is a random shift K lift, etc., etc. So random lift in general, you choose only the permutation choice is the random part. Okay, and easy observation, we don't need to worry about the degree of the graph because it remains deregular if the original graph was deregular. Okay, so since we use lifts we don't yet, but we want to use lifts to construct expanders, let's see what happens with expansion of the lifts. So here are some elementary observations. A lift cannot have a better edge expansion than the base graph. Why is that? When we take any set on the base graph, I'll give you a set with the same expansion. Just take all the K copies of the vertices in the set, both the edges and the vertices increase by a factor of K, therefore expansion cannot cannot be better in the lift. And it can also be shown that it cannot be much, like it cannot be horrible if you take K large enough. Here's what happened with edge expansion, but we are dealing with spectral expansion right now. And let's see what happens there. Here's an easy but important observation. The original eigenvalues of adjacency matrix of the graph G are also eigenvalues of adjacency matrix of the lift. Why is that? That's easy to see. Take an eigenvector f of the base graph, and for each vertex v, let's say f of v was the value of the eigenvector. Just now copy this value for each one of the k vertices in the fiber. So now this new f prime eigenvector has constant value on its fiber and equal to f of v. It's easy to see that this is an eigenvector of the adjacency matrix of the lifted graph as well, with the same exact eigenvalue. So these eigenvalues that already belong to G, we call them old eigenvalues, because sort of there's no hope for them. There's nothing you can do about them. Yeah, they're doomed. And we call the new eigenvalues the hopeful ones, the ones that we can hope to improve, to say something about. Okay, so what we learned from this previous slide is that the spectral gap can also not increase, since lambda 2 of G lambda 2 of G is an eigenvalue of the lift. Therefore, we cannot hope to get better lambda 2. But what we can hope is to not get much worse, or to not get worse at all. So what we would like to show, and what Friedman started trying to argue about 10 years back, no, not quite, I think, would like to keep the new eigenvalues bounded by actually the Ramanujan bound if possible. So fine, we sacrifice lambda 2 of G, we have it, we can't do anything about it, but if all the other eigenvalues are bounded by 2 root D minus 1 or something around there, then we can essentially preserve the expansion of the base graph when we lift. And if we can do the above, then we have a good algorithm to produce arbitrary large Ramanujan graphs. Here's the algorithm. Start with a small Ramanujan graph, k d plus 1, let's say the clique. Lift it, since the expansion doesn't change, or the spectral gap doesn't change. This is an assumption that these new eigenvalues are bounded by 2 root D minus 1. And you cannot do better than that. So start with a 2 root D minus 1 expander, lift it, repeat. You can do that as many times as possible. You can get arbitrarily good expanders, arbitrarily large good expanders. Okay? Any questions so far? This is I'll get to that. But this is if we knew that a specific way to lift gives you 2 root D minus 1 new eigenvalues, then we could do that forever. Even at random, we could do that if we knew what I'm talking about.
At random, we know we can.
Right, but the point. I'll talk about all of this in a second. Okay. So here is what has happened so far until this result on lifts. And most of the things have happened in the regime where k is large. The k tends to infinity with, it's larger, for example, than the number of nodes of the graph. And the results that I'm going to present in this slide hold with high probability in k. So you need to argue to have a n lift or more, where n is the number of nodes of the graph, for the following results to be true. So Friedman, in the paper that I've been mentioning, showed that all the new eigenvalues of any base graph are bounded with high probability by order d to the 3/4 if k goes to infinity with n. Then Linian and Putter improved that to d to the 2/3, order of d to the 2/3. Dariobair and Griffiths improved to order of square root d. Now we're getting close. And finally, Putter gave an almost optimal result of 2 root d minus 1 plus 1, which generalizes, yeah.
There was a result of linear and Bilu, which gave...
I'll get to that.
No, but it's not part of it. I thought it would be in the sequence.
It's not, because this is for large lifts.
Oh, okay, good.
Yeah. So I'll get to small lifts in a second. You always go like 2 slides ahead. Okay, so here's what we know for k equals large. And this is great. I mean, we know almost everything. Now we know the new eigenvalues are almost Ramanujan. Okay, we don't need much more. But why look at anything else? Well, here's why I look at anything else, because, okay, fine, I tell you a random end lift is almost a Ramanujan expander. Well, go ahead and randomize it if you want. I mean, good luck with that. There's not much hope to do something. It's just like saying, okay, construct an expander from random d-regular graphs already. So we would like to look at k equals small, possibly k equals 2, and prove something similar. Like, can we show that for any base graph, 2 lifts are with high probability expanding? And then there is hope. There is a way. I mean, not an exact way to construct Ramanujan graphs, but Bilio and Lineal have a way to give good expanders from such lifts. There are many issues here, but let me say first what Bilio and Lineal actually did do. What they said is, okay, if we take 2 lifts, for any base graph, there exists a 2 lift such that all the new eigenvalues are bounded by this root d log 3d. Square root d log 3d. This is an existential result. It can extend to hold with high probability on the number of vertices of the graph if the base graph is a good expander. But it doesn't say if we take any base graph with high probability, all the new eigenvalues are order root d log 3d, because it can't say that, and we'll see why. And in fact, this breakthrough I was talking about that showed that Ramanujan graphs of all degrees exist went with 2 lifts. So they proved that there exists a 2 lift for every graph that has exactly the Ramanujan bound. Okay, so all of those results are really great, and they advanced the field of expanders, but none of them says what happens with high probability, I mean, except for this sort of semi-high probability statement. None of this says what happens on average if you take 2 lifts, nor do we know how to find actually a good lift, with the exception, again, of Bilio and Lineal that extended this proof to a construction, which still gives the log 3, so the square root log 3d factor, which is sort of unwanted if you want to construct Ramanujan expanders. Okay, so let me show you what the results that I want to talk about are. I'm going to talk about results on 2 lifts and k lifts in general for shift k lifts, for any k. And also a nice byproduct of all of those would be a complete characterization of the eigenvalues of k shift lifts. So let me present this ugly picture now, which is the theorem that I want to talk about. So what we show in this paper is that if G is a d-regular graph and all its non-trivial eigenvalues are at most lambda in absolute value, let H be a uniformly random 2 lift of G, and lambda nu be the largest in absolute value eigenvalue of H, then this is bounded by order of lambda. So we don't have any log d factors, we don't have any assumptions on the base graph. So if the base graph is Ramanujan, if it's a clique, d plus 1, this could be order of root d minus 1. Or root d, I guess, doesn't matter if you have the order. And this happens with high probability in the number of nodes of the graph. And we get something stronger if the graph is expanding, but I'm not going to talk about this. And a similar thing holds for k shift lifts for any k. Very similar thing. In fact, exactly the same, just the probability changes. And I'll explain why those 2 things are essentially the same thing. But let me first remind you what we saw, that lambda nu is order of lambda. Order of the lambda, yeah.
So you cannot iterate it now?
Not at the moment. Yeah. Okay, so this is the result that I'm talking about from now on. But let's first see how optimal is this result. I mean, we saw before Bilio and Lineal showed root d log 3d, which is clearly not optimal because we get something stronger. But is this optimal, or can we get Ramanujan? Can we get something better? So there are 2 possible places where these theorems could be improved. One place is the dependency on lambda. As we saw in the large lifts case, there was no dependency on the base graph. We said any base graph, take an n lift at random, it's almost Ramanujan. Can that happen here? And the answer is no. Suspense. Okay, the answer is no. Why is the answer no? It can relatively easily be shown that, for example, if you start with a disconnected base graph, let's take n over d plus 1 copies of k d plus 1, then a random 2 lift of it with high probability has new eigenvalue equal to lambda equal to d. So we cannot hope to get any Ramanujan bound that does not depend on the eigenvalue of the base graph because we have very little randomness. I mean, in some sense, taking n lifts kills the base graph. Like, it's so much bigger. But here, we can show that with high probability. There still exists one that's Ramanujan, but with high probability, most of them are actually disconnected. So dependency on lambda is necessary. Then the second place that we could look at is, can that constant become 2 root d minus 1 instead of or rather, can it become lambda nu less than or equal to lambda rather than less than or equal to order of lambda? And experimentally, Dan Spillman has run, and Nikhil has run some experiments that show that about half of the lifts are actually Ramanujan and some of them are not. So we can't really do that with high probability either. So, I mean, yeah, we can improve our constant right now, which is not the best. Maybe it's like 1,000 million something, I don't know. But I don't even remember what the constant is. But we cannot really improve morally much in that sense. So in that sense, our result is optimal. Okay, so now I'm going to, unfortunately, the proof is really ugly and has very, very scary formulas. I'm going to try to sketch a little bit what happens and how to prove that in the last 15 minutes. I have a bunch of time. Okay, so here is the proof of theorem 1, which says what happens with two lifts. Amazing fact about two lifts, and as it turns out about K-shift lifts, which was given to us, was known, and it's actually easy to observe, is that these are equivalent to signings of the graph. What do I mean by signing? Well, take a graph, sign its edges, randomly or however you want, with plus and minus 1 signs. And let's denote AS of G the signed adjacency matrix, which instead of 1, when there's an edge, I have now the sign, minus 1 or 1. And it's immediate to observe that a two-lift and a signing are the same thing. I mean, they're equivalent. Why? Well, take a signing, and let's say the sign of edge xy was 1. Then I put the identity permutation as a matching between the fiber of x and the fiber of y. And if the sign of edge xy would be minus 1, then I would put the cross permutation. So maybe let me draw that. So we have this edge, and here's the corresponding part of the two-lift. If sine of xy is 1, then this is what happens in my lift. And if sine of xy is minus 1, then this is what happens in my lift. So it's immediate to construct one from the other. And this is great for us because now we know exactly what are the eigenvalues of the lift. They are the eigenvalues of A, as we saw before, of G, the adjacency matrix of G, union the eigenvalues of the adjacency matrix of the signing. So the complete set of eigenvalues of lift are characterized by these two matrices. And this is easy to see. This is like a sketch of the proof. We saw the fact that eigenvalues of G are eigenvalues of the lift prior to this slide. And now let's see that eigenvalues of the signed adjacency matrix are also eigenvalues of the lift. And what we do is we observe that the lift adjacency matrix is just this block matrix that has A plus AS in the diagonals and A minus AS in the off diagonals. And if U was an eigenvector of AS, then U minus U is an eigenvector of this matrix with the same eigenvalue. In fact, 2 times the previous eigenvalue, but 2 cancels out with that. So the eigenvalues of the eigenvalues of the signed matrix are also eigenvalues of the lift. So now if we wanted to bound anything about the new eigenvalues of the lift, we need to look at one thing, the spectral radius of AS, which is the largest eigenvalue of AS. Makes our life pretty easy, because instead of dealing with big matrices, I guess twice as big, now we deal with one matrix and only the spectral radius. We don't need to consider lambda 2s or lambda 3s or anything like that. Okay, so what we hope to show to prove theorem 1 is to show that the spectral radius of a random signing is with high probability bounded by something proportional to L of G. And this is the spectral radius by definition. So let me try to describe really quickly what bilineal did to to prove the existence of a lift of root d log 3d. Here's what they did. They used a very important lemma, which is called the converse of expanded mixing lemma. All it says is take a real n by n symmetric matrix, zeros on the diagonal, kind of like an adjacency matrix looking thing, and L1 norm of each row is at most d. If for all 0, 1 vectors this holds, so the ratio, almost the Rayleigh quotient, I don't know, it's not exactly Rayleigh quotient, but anyway, this holds, this ratio is bounded by alpha, then we can argue that the spectral radius of A loses a factor of log d over alpha, but it's bounded around alpha log d over alpha. So they use that in this way. They show fix u and v belonging to 0, 1, or I guess 0, 1 minus 1, but this is a technicality, so that with high enough probability, this holds. So this ratio is bounded by order root d log d. And now you can see where the log 3 to the third d comes from. Because you saw that this happens, then use Lova's local lemma to argue that there exists a single signing that for all uv, the same exact signing gives you this order root d log d ratio. And then conclude by the converse of expanded mixing lemma that I just showed you, that by another log d factor loss, the spectral radius of AS is order of whatever we had here times log d, which turns out to be that. So this is their approach. And in fact, this theorem is beautiful, like the converse that they showed in this paper. However, it has a couple of caveats, as for our purposes. The one is that there are two places where we lose a log d. I guess a root log d and an actual log d, which is pretty bad. And then this proof cannot provide high probability bounds. That cannot happen from this way of arguing. So we need a really more delicate analysis and a lot more things to happen for the theorem to come together. So here is what we do to remedy this problem. Remember, we need an upper bound on the spectral radius of the signed adjacency matrix. So look at the fixed vector x and just round it down or up to a vector that looks like plus minus 1 over 2 to the I. And it's easy to show that we can lose a factor of 4 and approximate the spectral radius of AS with just looking at vectors of this form. Then we consider the dyadic decomposition of y into vectors. That means that ui is sort of the 0, 1, minus 1 vector that had 1 over 2 to the I coordinate. And we easily write y in this form. And you can see that this sum is just the sum over all ij's of the corresponding terms. Bear with me in this couple of slides. I said they were ugly. Let's look at an individual term in this inner product. One of the ui and uj. So fix I and j and look at it. And s, remember, is a signing that now we choose at random. So over random choices of the signing, this term is just a sum of independent zero mean random variables. And easily, we can apply off-the-book Chernoff bound and prove that, in fact, the absolute value of this term cannot be much larger than root d log d times the supports of the vectors. Here, SU is the support of the vector. And this is so far what Piliulina used in their proof. That's the first part of the proof. And here's there are two immediate problems here, the log d and this support. If this support is small, then probability is not enough. So here's how we remedy the high probability problem. Well, very obviously, we look at small sets of small supports separately. So when the support of ui and j are small, then we just put a trivial bound and bound this by lambda norm of y squared. Not with high probability, always. This is just a completely trivial bound that always holds. And in fact, I want to draw the attention again to lambda. We argued before that lambda, the dependency on lambda cannot be avoided. And this is another place where we see that, because for small sets, we can see on the base graph, the edges that go out of small sets are governed sort of by lambda, if you look at expander mixing lemma. Okay, so this is the second place where we see that we really need lambda. But the nice thing about this is once we get rid of these small support sets, then we have high probability. So that's fine. We resolve this problem. However, we still need to resolve the log D problem, which is the harder problem. And here's what we do. Remember this sum, that we had these dyadic terms. And the number of terms in the sum is edges between the supports of these two vectors at most. And let's approximate them using expander mixing lemma. So now we'll use this as a bound on the number of terms in the sum. And just to remind you, I don't know, probably all of you know, but this is expander mixing lemma. It argues that for any graph, the number of edges between any two subsets are close to what happens in a random graph and close governed by lambda. So this is expander mixing lemma. Okay, so we use this thing to approximate the terms in the sum, and we look at two cases on which term of the expander mixing lemma approximation dominates the other. So the first case is when this is smaller than this, so one term dominates the other. Let's go back to the Chernoff bound that we had with the log D factor loss. We need the tighter bound clearly on the deviation of this term, because otherwise, we're done. So instead of log D, we just use log D times the ratio of the supports. And here's what we get with hyperprobability. I'm just flashing this here. It's really ugly, and I apologize for that. But this turns out to be yeah. This turns out to be exactly what we need for the union bound to work. And now for all the terms psi j such that this term dominate the other, we can use a union bound and argue that with hyperprobability, everything works. And I want to note that here is an important point, that one of the problems that bilineal had is that when SUI and SUJ were different in size, very different, then is when they get like a big problem and discrepancy, and the log D factor was one of the places that it came up. So this takes care of this discrepancy by adding the ratio. Okay, so case 2 is when the other term dominates the other. Well, there is another hidden case in there where we can deal with easily when I and j are far apart. Just trivial bound again that holds always. But so let's look at I and j close together. The remedy we found for this part is, instead of looking at each term of the sum, we look at a sum of terms to sort of convert the sum of square roots to a square root of a sum type of thing. And again, if we didn't use this sum, then each term would be counted log D times, or a half log D times, and then we would get a log D factor of loss. And this is the second ugly thing that we get for this, or beautiful, I guess, thing that we get for this case. I guess I have a few minutes, so let me put everything together, and you get the proof. I don't want to go more into this proof because it's mostly after these 3 observations and remedies, it's calculations and they work out. I do want to say what happens with the generalization of the K shift lifts, because this is something that I think is pretty beautiful, actually. So now a shift lift is what you expect to be. Instead of choosing any permutation between the fiber of x and y, you choose a shift permutation. This is, for the unique game sort of notation, x minus y equals c mod k. It's a constraint of this form. Okay, so these are shift lifts, and a 2 lift is a specific case of a shift lift. And let me remind you what worked for us. Why was it good to? Why were we able to argue about the eigenvalues of 2 lift? Was because we knew what the eigenvalues were. We had to look at the adjacency matrix of the sine graph and bound its spectral norm, spectral radius. Okay. Can we say the same thing for k-lifts? There is no such, at least currently or previously, there is no such characterization. However, let me define a generalized type of signing. So let's pick a parameter t for now. And for each edge of the graph G, let's sign it by 1 power of t. So t to the 0, 1 to k minus 1, if we have a k shift lift. And let's call A, parameterized by t, to be the signed adjacency matrix. It turns out that the eigenvalues of the lift adjacency matrix for k shifts are exactly the union of the eigenvalues of A omega, where omega is the kth root of unity. So we have k different matrices, k times n eigenvalue, so it's k times n eigenvalue. This gives the complete spectrum of the lifts. And now our job becomes easy, because all we need to do is to bound the spectral radius of each of those matrices separately, and we get the same result pretty much with the same argument. I mean, in fact, we prove this, and then 2 lifts is a special case. Okay, so I have a couple of minutes for open questions. If you have any questions, ask me, but I'm going to move to future directions so far.
Yeah, so what happens to the curve of the graph when you do a lift or a shift?
To the what?
Curve of the graph, the length of the shortest sample.
I mean, it depends on how you lift, right? You could take the identity lift and then you have disconnected copies of the
so
same
when
graph.
you take a random lift.
I'm not entirely sure. Yeah. So the main open questions that I found, and I mean, in fact, few of them are the reason why we got there with this result, is what percentage of lifts is exactly Ramanujan? Is it 51% that I don't know, 52%, or something else? I don't know. We can't, there is no clear methodology to argue about when is something exactly Ramanujan right now. Then a similar question, if you start from any base graph, how likely is it that you get exactly lambda in the lift? We don't know how to say that, but if we did, that would be great. And the main question that all of this sort of business started from is how can we use this to build good expanders? We even, at the moment, don't know how to use this to build expanders with order of lambda loss. Because bilineal, the log D factor there allowed them to actually turn it to a construction, but if we don't have the log D factor, we can't even turn it into a construction right now. So we don't know how to build expanders from this at all. Yeah, okay. Thanks.
So the Allen-Bopana bound bounds the first non-trivial eigenvalues, at least 2 reduce something. Do you have a similar bound for the largest new eigenvalue of a lift? Does it also have to be bound?
Yeah, I think Joel Friedman, in one of these papers that I mentioned, has, it's either a very recent work of his or, I mean, he definitely has a bound on one of his previous papers, but I think I was talking to him a few months ago, and he mentioned that he has that for the lift, like the Allen-Bopana type of bound.
I just want to mention another paper that in a different way goes close to the Ramanujan bound. It's a paper of Amnon Tashma and Ben Aroya. So one of the problems with, even if this was deterministic and turned into a construction, it's like bilineal do. It only generates polynomial size graph in polynomial time, where we often need exponential size graphs, right, and described in polynomial time. Zigzag can do it, but not with the Ramanujan bound.
Right.
And what they did, Tashma and Ben Aroya, was to massage zigzag so that it does give exponential.
What bound does it give?
The bound is square root t times something that's small, but it's not polylog, it's 2 to the root log t.
Okay.
Yeah. So
right.
You can like it or not. No, it's like the zigzag thing. We got d to the 2/3.
You know, what's the saying that size doesn't matter, just the quality, right? So we don't care about exponential, we just want Ramanujan. No, I mean, I'm joking, but yeah, I was not very aware of this paper.
Further questions?
So how do these lifts compose? And then how does a k lift followed by a k lift differ from a k squared lift?
You mean a 2k lift? Or k squared, yeah, sorry. I think not all k squared lifts would be like a combination of 2 operations. So the other way, if you take a 2 lift, let's say, all 4 lifts are not, either, I don't know how to explain that. Maybe picture would be better. yeah, I guess I'm not even sure if picture is very better, but not all four lifts are combinations of two lifts. Pretty
No, I'm
much.
saying like in terms of expansion. So
So you mean how, if we repeat the operation, what happens, or?
I mean like, so if we do a 1 k square lift, so can the expansion be much better than doing a k lift followed by a k lift? Oh, I mean the other way.
At random, you mean?
Yeah. Or,
I mean, if you lose nothing, if you manage, since there exists a lift that preserves Ramanujan bound, then it makes no difference. In some sense, you can get as good expansion with either operation. But if you do it randomly, I don't know.
4 o'clock the next talk? Or?
I think it's 4:15.
Anyway, there's a good period of time until the next
4:15, right?
Yeah,
4:15.
Let us thank Alexandra.